All right, here we go. So starting off very simply, we're not going to cover everything in chapter 3, but we'll get through quite a bit of it. So some things to note about this is that if you're not familiar with vectors, many of you know already though, but if you haven't dealt with them before, we associate them with having a magnitude or size as well as a direction. The other thing too is you will want to be aware of the direction, and your starting point is going to be called your initial point. And then where that vector ends up is going to be your terminal points. They're using initial point and terminal point as our terminology for this text. So here's the other thing that you're going to want to be careful of, because we're going to be dealing with a lot of things in this textbook. So you do want to remember your notation. So vectors are going to have boldface lowercase letters. So here's where I have seen that some students have kind of messed some things up because they forget that we do have scalars, but those are going to be lowercase. They're not going to be bolded, and those are going to be usually in italics. So make sure that you're not mistaking a vector in bold for a scalar. I've had students do that before. So like I said, a vector is going to have initial point A, going to a terminal point B. And here is where we consider vectors to be equivalent if they have the same magnitude and they have the same direction. So we'll call them equivalent or equal. So if V and W are equivalent, they're going to be equals. So what do you notice though about these particular vectors? What's interesting about them? Yeah, so the same size, same direction. They might have different origins. So they don't necessarily have to have the same origin point to be considered equivalent here or equal. So you'll notice like this one has its origin point here. This one has its origin point there. What's another thing you notice about these as well? In this particular case.
Pointed to the right.
They're all, yeah, they're all going off. Yeah. What's interesting, yeah, you could say too that all these are parallel since they all have the same direction. So just keep a note of how vectors are described in this text. So the other thing too, I think this one's obviously kind of intuitive, a zero vector. Obviously the initial and the terminal points are going to coincide. Its size or magnitude is 0, so just going to end it. We're just going to call it, we're going to denote it by 0 in bold. So that's going to be the 0 vector here. So hopefully some of you have seen this parallelogram rule for addition of vectors. Maybe you guys are pretty good at drawing this, I would assume. So here you have vectors V and W. You're going to map out your little parallelogram here. And then you're going to make sure that your sum then is going to start from the origin point of both of them and then go to the vertex of the opposite end for that parallelogram. So here, this through the middle of the parallelogram is going to be your V plus W. So you probably have done that time and time again. So let's see what else we got. There's also the triangle method. Have any of you guys kind of done this as well?
Yeah.
Okay. So here you're kind of going tip to tip. So here you got V here, then you're going to have another vector W that you want to add to it. So you're going to put the initial point of W at the terminal point of V. W is going to extend out. Then to get your sum, you're going to start from the initial point of V and go to the terminal point of W. And you're going to get your sum V plus W. So all I get. So you could do it either the parallelogram method, that's easier for you to visualize. A lot of people find the triangle rule for vector addition a lot easier. So which one do you guys use? Just out of curiosity.
Tip to tip.
Oh, you do the tip to tip? Okay. The triangle. Okay. All right. So this is vector addition rule. So one of the great things here is that you can see it with the triangular method here. As well as the parallelogram rule. But you can see that V plus W is going to equal W plus V. So these are going to be, whichever order you put them in, they're going to end up equaling the same amount. So you could either start with V, then you have V here, then you're going to add W to its tip, then you're going to draw your sum from the initial point of V all the way up to the terminal point of W. So you're going to get your sum that way of V plus W. Or you could decide to go the other order. You could go W, then you put the tip of initial point of V on the terminal end of W, and then you once again take your sum by going from the initial point of W all the way up to the terminal point of V. So either which way you want to go, you're going to end up with the same results. So here, same other vector subtraction. We say that the negative of vector V is going to be denoted here negative V. So just realize that if you see negative V, it's going to be the same length, but it's going to have the opposite direction. I think that's pretty intuitive there. Here, if you want to do subtraction and you have a vector W and you want to subtract V from it, that will be equal to adding the negative of V. So that's kind of useful as well. So that one's a little bit interesting to go ahead and draw. So does anybody want to draw this figure on how you might subtract V from W? What would that parallelogram look like? Or what would that triangular method look like? Anybody wants to try it?
You said W minus V?
Yeah.
So,
Yeah, you want to go try it?
like on the board?
Yeah, why not? So what can you do?
It was W minus V, right?
Yep, W minus V. Oh, okay. Yeah. So you did it that way? How would you do it if you wanted to do a parallelogram?
Yeah.
It's just a triangle.
I don't do the parallelogram. Is it just? Yeah.
Yep, you just keep, yep. Yeah. So there you go. So it depends on like what is more intuitive to you. Looks like you guys are pretty well versed in this. So is anybody like this is the first time that they're seeing vectors? Nobody? Everybody's seen them before. All right, so this should be pretty easy. So then you guys should know all of this as well. So here, if you got your scalar multiplication, this is pretty self-evident here. So here, if we have this original vector V, what if we multiply it by a scalar of 1/2? What would happen? What happens to it? Yeah, magnitude reduced by 1/2 there. Here, what's happening in this third one? Yep. Yeah, you got negative V, so now it's the opposite direction. What's happening in this one here? Yep, magnitude is doubled. Here, you have both the opposite direction and your magnitude is tripled. So all that kind of easy stuff. All right. Ooh, so here is something that maybe people are not aware of, but in this text, collinear and parallel are going to mean the same thing. So just realize that for this textbook, if two vectors lie along that same line, they're collinear, but if for some reason one of them, even though if they have the same direction and they're parallel and their initial point is changed, then even if they're parallel, they're also going to be equal to one another. So parallel and collinear are going to mean the same thing here when applied to vectors. So here we've got sums of 3 or more vectors. We've got the associative law. We've seen this probably before with algebra. So it doesn't matter which order you add them in. You could add V plus W first, then add U to it, or U plus V and add W. Yes?
On that previous slide?
Yeah.
So the second image, that's also considered collinear?
Yes, so in this case, in this text, collinear and parallel are going to mean the same thing when applied to vectors.
Okay.
Yeah.
All right. Thank you.
So yeah, so you're gonna, that is on page, if you don't believe me, that is gonna be on page 149. So we are going to assume that parallel and collinear are going to mean the same thing in this instance when we're going to apply them to vectors in this textbook. So that'll be one good thing to keep in mind. So then we have the associative law for addition. So you can see all the different ways in the textbook if you so choose. You can kind of map those out, either which order you want to go. And then here is where we're going to also call them by different things. So vectors are going to be kind of described by their components. So V is going to have the components, for instance, if we're talking in 3D space here, it's going to have the components V1, V2, V3. So you can kind of refer to them as either components of vector V, or if you so choose to visualize this as a point, you would call that the coordinates of that point. So you'll see kind of both terminologies throughout the text. Most of the time, we're going to probably be referring to vectors and calling these components. So obviously, if you have this in 2D space, you're going to just have the two components here. If you're in 3D space, you're going to have the three components. So often written as such. So here, this is vector V. Here's this how they would have a notation for its different components. It's usually with the same letter with the subscripts of numbers. All right. So here, another way that we kind of represent vectors is by their origin and terminal points. And so we have a way of kind of visually describing that, where here P1 is going to describe that initial point. P2 is going to be that terminal point. We can kind of quickly denote this vector as being P1 to P2, written as such as this, but we just need to realize that P1 and P2 both have their own components to it. And so we're going to be as we go through this, we're going to be looking at vectors where their initial point is not at the origin. So yeah, we could get lucky where we have all these vectors that originate from 0, but that is not going to be the case most of the time. So we're going to be learning how to kind of manipulate vectors whose initial point is not at the origin. We had been previously before, though, dealing with these vectors that were very, very easy because they had their initial points at 0. So here's what it would look like in 2 space, and then here's in 3 space or 3D. So you can kind of, if you can kind of see the very faint cube, that kind of helps you kind of visualize this in 3 space here. Here we have the components V1 and V2. There's only 2 of them for 2 space that are going to describe this vector V. And then we have 3 components, obviously, in 3 space. So the next thing, though, that we do want to go ahead and go over is what if, just what if, we happen to run across the situation where the vectors, they don't have an initial point that's at the origin. What if you have this vector that's just hanging out here in 2 space? Its initial point is not at the origin. So do remember that we can represent a vector V. Now, keep in mind the other thing that we also learned about vector notation is that they are going to be lowercase letters. They are going to be in bold. And then when to easily kind of represent a vector that has an initial point and a terminal point, we can basically list those points. So here in this case, they're called P1 and P2. And then we have this little arrow that we've drawn over them to indicate that we are talking about a vector. So just realize that. Now we might have this situation, like I said, where this vector, its initial point is not at 0. So one thing that we do want to note is that it's very easy to kind of calculate those components for our vector V. And so we are going to be looking at this particular situation. So here we have our P1. You could even, if you wanted to, you could relate it to the origin. You could say that this particular vector, if you wanted to start at the origin, you could even call this as OP1. Draw a little arrow over the top. And then you might even characterize our vector V with another vector here called OP2. And you'll notice that V then is going to be then in between those 2 vectors. So we could say then in this case that V equals our P1, P2, and that's going to equal OP2 minus OP1. So here we're trying to figure out this V here. Now we could relate this vector V to the origin by drawing these other vectors here, OP1 and OP2. You're basically taking the difference between them to get that V. And so we'll be able to solve for our P1, P2, or our V. And all we have to do, it's really, really simple. If you've looked through your section, is basically you're going to take the terminal point P2 here. So you're going to say x2 minus our x1 here from our initial points. So that would be the first component of our vector v. And then our next component would be going ahead and taking y2. So here, y2 minus our y1. And those are going to be your components for the vector v. So really, really, really easy there. Now, if you wanted to go ahead and describe that in multiple dimensions, you would just kind of keep going along the same vein. You could certainly do this in 3 dimensions. Whoop, I don't think we're going to show it here. Whoop, there it is. So here you have it in 2 dimensions, x2 minus x1, y2 minus y1. Here we have it, if this was in 3 dimensions, you'll notice that there's now a third component, z2 minus z1. So pretty simple stuff there. So here they have an example here where we have a vector v described by p1, p2. So here we have some initial points. You will notice immediately that this is now dealing in 3 space because here we have 3 components to our initial point p1. And then we got 3 components for our terminal point P2. So like I said, to be able to figure out what is that vector V, you'd be simply taking, I'm going to go ahead and write it in notation here. And then we'd be doing that simple thing here where we're going to be taking our, I'm going to go ahead and write it in components here. So here you're taking P2 minus P1 for the first component. So we'd have 7 minus 2 and comma. So now we're going to go to our second component. So now we have 5 minus -1. And then for our third component, now we have -8 minus 4. So all of that is going to end up giving us the components for V. And we should get 5, 6, and -12. So simple stuff. Now you would just simply carry this out as many dimensions as you have in a particular problem. So this was pretty easy. This was 3 space, so we had 3 components, but certainly it could be more than that. But this is pretty easy in those. All right, so we will go ahead and I think we've kind of covered most of what is in section 3.1. So you want to make sure that you know about whether or not vectors are equal and equivalent. Obviously, in that case, their components are going to be equal. So here, you would also want to remember that in terms of describing your n space, you're going to be having your ordered n tuples again. So that's going to be similar to what we've seen before. And so here we're going to be talking about real space is going to be denoted by a large letter R in italics. You'll see a little superscript n. That's going to indicate to us what space we are dealing with, to what dimension. So we've seen like 2 dimensions, 3 dimensions, but this could certainly be much greater. So you're going to want to look for that superscript to know, how many dimensions are we dealing with. So like I said, here you're going to want to look at whether or not 2 vectors are equivalent. So here's a vector v described by its components, v1 through vn. Here's a vector w, which would be w1 through wn. And so these are going to be equivalent. You can also say they're called equal if the components of v and w are the same values. So here we're going to say it's going to say v equals w. So you're going to go ahead and you'll see some different problems like this. It'll ask you, you should be able to glance right at it from inspection, whether or not vectors are equal or not. So not too big a deal. Looks like there it says they're using the screen as if we were. So that's good. It looks like they're in the room and they're going to be using the screen. So awesome. All right. So don't forget, you're going to have different operations. You definitely want to make sure that you check out those. Those are going to be definition 3 on your page 154. Obviously, you can easily add 2 vectors together. So if we have a vector v, we've got a vector w. Basically, you're going to be easily just adding their components together all the way through whatever dimension we're talking about. Here we've got our scalar k. Well, that's easy enough. We're going to be multiplying all the different components by that scalar k. If we have a vector that's in the opposite direction, all those different components are going to have a negative sign in front of them then. Then here we can think about subtracting one vector from another as being the same as adding the vector in the opposite direction. So however you want to visualize that. So here you're going to want to make sure that you know your theorem 3.1.1. Those are going to have some very obvious rules that you're probably familiar with. Certainly all of these are kind of self-explanatory. You'll want to look through them. The other one that you do want to make sure that you do recognize is that we can actually write vectors in terms of linear combinations of other vectors. So here you can see here if W is a vector in real space, then W is said to be a linear combination of the vectors v1, v2 through vr if it can be expressed in this form. So just realize you might want to go ahead and look at definition 4 to remind yourself of this, because we're going to see this again, hint, hint. We're going to do some problems where you're actually going to have one vector be a linear combination of some other ones. So we'll be seeing that again. The other thing we will have is some other alternative notations for vectors. So this first one, we call this a comma delimited version or notation of a vector. So here you're kind of writing it in terms of its components all the way through whatever space it's up to. Here you will have a vector expressed as a row vector. So don't forget, we're going to be relating these vectors to matrices. So here, this vector would be a row vector. You could even consider this a row matrix. Here you can express a vector as a column vector, and then this would be a very simple column matrix. So just some things to kind of note for later.